This is a week that doesn't come easy to a lot of students. It's not real intuitive, so hopefully this video will help you a little bit. But an exponential function is one that can be written in the form of y equals b to the x, where b is a positive number other than 1. So we're not going to talk about negative numbers raised to a power in this section. We're just going to talk about positive numbers raised to a power. The best way to graph an exponential function, in my opinion, is to just set up a little table of values and simply choose a variety of values for your x, substitute them in for your y, and calculate what the results will be. So if I were to ask you to sketch y equals 2 to the x, I like to just pick some fairly small numbers, usually -3 to 3, and plug them in. And then you're going to solve for y equals 2 to the x. So we'll have y equals 2 to the -3, y equals 2 to the negative squared power, y equals -2 to the 1, 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. So we solve and we come up with this set of ordered pairs, because this gives you your x and this gives you your y. Then you can graph these. You can start plotting them. You can see -3 1/8, -2 1/4, and so on. And I get some points that look about like that. And when I graph them, you can see our exponential curve sharply turns upward. All exponential curves are kind of look like this. Some can be curved up, some can be curved down. They can be a lot of different orientations, but they're basically going to look like half of a parabola that we talked about last time. So here is some different orientations that you can see of exponential curves. And again, if I ask you to sketch y equals 0.75x, I would just put in some values for x. I picked a wider variety this time, -10 to 10. You can pick whatever you want that helps you see the curve. But because we had a fraction in our original equation, I wanted to use something that would make my numbers a little bigger. So I used -10 to 10. To solve these, you're going to need a calculator with a y to the x key, or one that at least has a caret that will let you do multiple powers of a value. And when you solve these, you're going to get this set of ordered pairs, with this being your x value and this being your y value. If you graph this equation, you can see that it looks something like that. Still very much with the same shape of an exponential function. Exponents and exponential functions can also be part of a larger equation. For example, sketch y equals 1 minus 2 times 3 to the x. Again, I like to just do it by choosing a variety of values for x and plugging them in and solving for my values of y. And when we graph this one, it looks something like that. Now, a special type of exponential is e to the x, or a natural exponent. Now, e is something that's very much like pi. It's just a given number, and we're going to use 2.718 in this class for e. So the graph of e will look very similar to the other graphs in this section. And it is often used to model population growth or rates of change with this given formula right here. P equals P sub 0, meaning P at time 0, population at time 0. And K is going to be the difference between the birth rate and the death rate, or in other words, K is going to be your rate of change and t is at some point in time in the future. A classic problem like this of a population growth example would be, in 1970, the population of the United States was 205 million, basically, with a birth rate of 18.4 per thousand and a death rate of 9.5 per thousand. What do we estimate the population will be in 2012? Well, P sub 0 is our population at time 0, and that's what was given to us in the problem, 205,052,000. The birth rate is 18.4 out of 1,000, or 0.0184. Remember, move that decimal point back 3 places. 1, 2, 3. And the death rate is 9.5 per thousand, or 0.0095. K is going to be the difference between the birth rate and the death rate, so 0.0089. And then we are ready now to substitute everything into our formula. The population estimate in 2012 is going to be 205,052,000 times e raised to the k t. So when you multiply 0.0089 by 42 years, because from 1970 to 2012, that is 42 years. So that's where we get the 42. And that sum is 1.45325. I try to write all this out so you can check it on your own calculator. Then when you raise e to the 1.45325, you will input that into your calculator as e and then hit the caret key and 1.45325 and then enter or equals. And then when you multiply that solution by 205 million, you should get 297,991,096 for the population in 2012. So that was kind of a brief explanation of exponential functions. I want you to look at the problems on the middle of page 25, which I have also attached to the notes. Numbers 1 through 7, they're right here in the middle of the page. And then on the pages that follow are the solutions. So hopefully that gets you started. If you have any questions, please just let me know.